At the beginning of 1905, a 25-year-old office clerk lived in the Swiss city of Bern in this small apartment of the Kramgasstrasse. He was newly married and devoted his free time to think about scientific problems, hoping to publish some new discovery in the most important physics magazine in Germany, the Annalen der Physik. Before and after his obligatory 8-hour work shift, Saturdays included, the clerk used to take walks around Bern, discussing with his friends the ideas he was developing. This way, the pleasant capital of Switzerland, with its narrow streets, gardens, river, its bears, and above all, its clock, was the scenery of one of the most important scientific revolutions of modern times. Because when the secrets of the clerk were finally revealed, they transformed the way we understood the universe forever. Five Secrets of an Office Clerk. The clerk was born in Ulm, in the south of Germany, in 1879. His mother played the piano, and his father worked at the most modern business in those days, electricity. As we can see from his final French examination in a secondary school in Aarau, Switzerland, at 16 years old, he had one thing very clear. Well, as a matter of fact, two things. He would be very bad at languages, and he wanted to dedicate his life to science. He once said, "I'm much attracted by a certain independence offered by the scientific profession." In 1896, he entered the Polytechnic School in Zurich to be trained as a teacher in physics and mathematics. By the summer of 1900, he had already met the men that would become his two best friends, had fallen in love with a classmate who would be the mother of his children, and had managed to irritate most of his teachers. He obtained his diploma with the worst grades of his generation, and he was the only graduated student who didn't get a position as a teacher. He sent dozens of letters that showed his lack of modesty to several German and Swiss universities asking for a job. As he did not get any answer, his humble conclusion was that academic world didn't deserve him. A visit to Bern. Finally, almost 2 years after graduating, one of his friends got him a job, not as a teacher, but as a clerk officer. He was appointed technical expert 3rd class at the Bern Patent Office, where he moved to in January 1902. He had to examine the applications for new patents. In order to earn extra money to pay the expenses he had as a newly married man, he advertised in a Bern newspaper offering private lessons in physics and mathematics. A philosophy student responded. Soon, the lessons became an excuse to discuss themes of science and philosophy, and together with another mathematician friend, they created an informal academy, which they very formally named Olympia Academy. During their meetings and walks around the city, they talked about the books they read together, but what they enjoyed the most was to discuss their own papers, which, in those times, were not that many. At the beginning of 1905, one of the members of the Olympia Academy left Bern, and our clerk wrote him one of the most famous letters in the history of science. Not because of its refined style, but because this is the first reference we have about the papers this man was writing.
Was machen Sie denn, Sie eingefrorener Walfisch? Sie getrocknetes
What are you up to, you frozen whale? You smoked, dried, canned piece of soul. Why haven't you sent me your dissertation? Don't you know I'm one of the 1.5 fellows in the world who would read it with interest? I promise you 4 papers in return. The first one is very revolutionary. A year later, The 4 papers of the clerk had become 5. All of them were accepted and published by the famous magazine Annalen der Physik. But to his surprise, scientists didn't seem interested in his work. The cold silence that followed the publication of his papers, wrote the clerk's sister years later, was a bitter disappointment to him. Everything seemed to indicate that the clerk would spend his life as a clerk, and this would have been a total waste, at least of his name, because if somebody had the ideal name to become a famous scientist, was him. The clerk's name was Albert Einstein. Unlike many papers published at that time by the Annalen der Physik, which are not totally forgotten, the papers written by the 25-year-old clerk had something that distinguished them: the contempt, to use his own words, to the collection of prejudices that we call common sense. A feature that one of the few physicists that read the papers when they were published did not overlook. In part, he read them because he didn't have much of a choice. He was the editor of the magazine, and his name was Max Planck. In 1905, Max Planck was one of the most recognized physicists in the world, and luckily for Einstein, Planck had not received one of his letters asking for a job. He was a professor at Berlin University and had built his career successfully applying to physics what in those times was considered common sense. Few people in the world have believed so much in common sense as the physicists at the beginning of the 20th century. And why shouldn't they? Thanks to common sense, they had discovered everything that was to be discovered. The carriages that didn't need horses, and the crystal bulbs that produced light without fire showed that the mystery of electricity and magnetism was solved. And the powerful railroads showed that the secrets of heat were dominated by thermodynamics, the branch of physics in which Max Planck had specialized. For many years, his research, partly financed by the German steel industry, had focused on one of the few phenomena that nobody understood very well: the way in which hot objects emit light. At steel foundries, it is common to calculate iron temperature based on the color of the light it emits. For instance, when liquid iron comes out of a blast furnace at more than 1500 degrees centigrade, it mostly emits an intense yellow light. But when it gets colder, the light emitted gets redder and redder. By the end of the 19th century, physicists had performed very accurate experiments that related the light pattern emitted by an object with its temperature, but no one had been able to explain those results using the known physics laws. Until 1901, after several tries, Max Planck published in the Annalen der Physik a mathematic formula that matched perfectly with the experimental data. His formula, though had a little inconvenient, it openly contradicted the common sense. Planck knew that the light emitted by a hot object transports energy far away from the object, and the trick he came about to make his formula work was the absurd idea that this energy can only be liberated in indivisible small packages that he called quanta. He thought that there is a minimum quantity of energy that the hot object can lose when it emits light. And if it's difficult to imagine energy, it is much more difficult to imagine it in small packages, and even more for a scientist like Max Planck, trained in the 19th century physics, to which the idea that there was a minimum quantity of energy that couldn't be divided more was unthinkable. It was something so bizarre, so distant from common sense, that Planck himself was sure that sooner or later there would be someone who would apply in a clever way the laws of physics known until then, changing his quanta for something better. He didn't count on the fact that on March 18, 1905, as editor of the Annalen der Physik, he would receive a paper that suggested exactly the opposite: to apply Planck's concept of quanta in an intelligent way, changing the laws of physics known until then for something better. The paper was signed by one Albert Einstein. The paper was signed by one Albert Einstein. Einstein was so proud of his paper that when he described its contents to Conrad Habich, his partner at the Olympic Academy, in the famous letter in which he called him Frozen Whale, he assured him that this was something very revolutionary. The theme was the nature of light, which in principle didn't seem very revolutionary, because by 1905 the nature of light was considered a problem practically solved. Light was an electromagnetic wave. At the beginning of the second half of the 20th century, and after centuries of experiments and speculations, Scottish physicist James Clerk Maxwell formulated a theory that successfully explained electric and magnetic forces based on the idea that electric charges and magnets modified the space around them, creating what we know as electric and magnetic fields. From his formulas, he concluded that an oscillating electric field can generate a magnetic field and vice versa, so the combined vibrations of these fields propagate freely through space. Maxwell called these traveling vibrations electromagnetic waves. And to his great surprise, when he calculated the speed at which they traveled, the result matched perfectly the speed of light, which by then had been very exactly measured. He then concluded that light is no more than electromagnetic wave, that the color of light is related to its frequency, that these waves can come in an endless range of color, and that the immense majority of them are invisible to us. 20 years later, this extravagant prediction was experimentally proved by German physicist Heinrich Hertz, who was able to generate and detect the colors of invisible light, first called Hertzian waves and now called radio waves. At the beginning of the 20th century, Guglielmo Marconi used these invisible waves of light to make wireless transmissions from one continent to another, and although they didn't understand them this way yet, physicians all over the world used other invisible waves of light discovered by physicist Wilhelm Röntgen in 1895, the X-rays. So at that moment, no doubt that light was a wave, and that was almost like doubting about progress and civilization. But this was precisely what the technical expert third class from the Bern Patent Office dared to do in his first paper of 1905, which has the bombastic title "On a Heuristic Point of View about the Creation and Conversion of Light." The revolutionary idea Einstein proposed was based on applying to light the same techniques that at the time were successful to explain the properties of gases, which made possible that trains moved, ships sailed, and zeppelins flew. It had been discovered that the best way of understanding the behavior of gases was to consider they are formed by a big number of moving molecules. Since in practice it is impossible to calculate the position and speed of millions of molecules, Maxwell himself, and later on the Austrian physicist Ludwig Boltzmann, developed methods to study very big groups of moving objects using probability techniques. Through these methods, it was possible to understand, for instance, that a gas temperature is really the consequence of the average speed of the molecules that form it. Lectures about the Theory of Gases by Ludwig Boltzmann. Since he was in college, Einstein was interested in these theories, but it wasn't until 1905, after he read the works of Planck on the energy quanta, that a simple yet fascinating idea struck him. If the assumption that gases are formed by molecules made it possible to explain many of their physical characteristics, why couldn't we think that light was also formed by particles? The result was amazing. Thanks to this idea, Einstein was able to clarify many phenomena that the electromagnetic waves theory had not been able to explain. On the determination of Planck's quanta. First of all, he could finally give a physical interpretation to Planck's mysterious formula which described the color of hot objects. The reason why the energy emitted in form of light comes in small packages, as Planck suggested, is that light itself is literally made up of small packages called light quanta by Einstein, and that now are known as photons. With this light quanta, Einstein also explained fluorescence, the phenomenon that makes possible for some materials to absorb light of a determined color and then emit it in a different one. This was very popular in alarm clocks and now is the basis of fluorescent lamps. Besides, Einstein solved one of the problems commented by everybody at the time, the photoelectric effect. The photoelectric effect is to convert light in electricity, and it caught the attention of physicists at the end of the 19th century, when British scientist J.J. Thomson discovered some small particles he called corpuscles, but the rest of the scientific community called electrons. Even though Thomson thought his corpuscles were useless, soon it became clear that the electric current which traveled through the wires that were beginning to light cities and move tramways was precisely made up by these corpuscles. Soon, scientists began to look for electrons everywhere. And in 1902, Philipp Lenard, this smiling man that would end up being Hitler's favorite physicist, found them precisely in the photoelectric effect. Lenard observed that when projecting light of a certain color on a metallic surface, the surface emitted electrons. As every physicist of his time, Lenard thought light was a wave, and that if the intensity of the light projected on the metal surface was higher, the speed of the electrons emitted would be higher too. But to his surprise, this didn't happen. The increase of intensity made possible to detach more electrons from the surface, but the speed of each one of them didn't change. In his paper, Einstein showed that with his light quanta, it was possible to explain in an elegant way this apparent contradiction. If the light that's projected on the metal surface is made up by particles, then the energy of a single light quantum is absorbed by a single electron, and this determines the speed at which it escapes from the surface. An increase on the intensity of light is equivalent to project more light quanta, and this multiplies the number of electrons that come off the surface. But the speed of each one of them doesn't change. Photoelectric effect was commercially exploited for the first time during the 1930s, when elevators began to use photoelectric cells to keep the doors open when passengers came in and out. But unemployed lift operators were not the first victims of light quanta. The first one was the common sense. Because even though Einstein's revolutionary idea explained very well the creation and conversion of light, its optic characteristics were still perfectly explained by the assumption that light is formed by waves. And if it seemed really complicated to determine whether light was a wave or a particle, things got worse when physicists became aware that this was not only a problem of light, but of everything around us. Mostly, this conclusion came out of the results of the next two papers Einstein had prepared for the Annalen der Physik. Einstein's house. My second paper, wrote Einstein in the famous letter to his friend Conrad Habicht, is a determination of the true size of atoms. He finished it on April 13, 1905, but he didn't send it directly to the Annalen der Physik, but to a Zurich university to obtain a doctorate degree. A new determination of molecular dimensions. Although this work contains enough mathematical formulas to be accepted as a doctoral thesis, it can be summarized in a very simple way. Einstein was trying to find a method to refute the most important German scientist with a spoon, a cup of coffee, and a sugar bowl. Although 19th century chemists were certain that matter is made up of atoms, the idea was not very popular among physicists. Important scientists like Ernst Mach, Wilhelm Oswald, and Max Planck himself thought that if nobody had seen them, it wasn't necessary to believe in their existence. But Einstein not only believed in atoms, he also proposed a way to measure their size, observing what happens when we drink a cup of coffee. When you add sugar to the water in a cup of coffee and mix the contents, the mixture becomes thicker and it is more difficult to move the spoon. This characteristic is called viscosity, and it can be measured. The more sugar you add, the bigger the atoms that make up these molecules will be. Einstein imagined that sugar is made up of a huge amount of small solid spheres and found a formula to calculate their size based on the viscosity of a mixture of water and sugar. The dimension of the spheres would be a good estimate of the size of the molecules that make up the sugar, and therefore a way of measuring the size of the atoms that make up these molecules. With the experimental data he had, he calculated that sugar molecules must measure around 5/10 millionths of a millimeter. That, of course, if molecules and atoms really existed. Something Einstein could prove very soon, because 11 days after he concluded his second paper, he sent the third one to the Annalen der Physik with the concise title On the Movement of Small Particles Suspended in Stationary Liquids Demanded by the Molecular Kinetic Theory of Heat. Oh. In it, he mathematically analyzed these strange movements that a British-Scottish botanic called Brown had discovered at the beginning of the 19th century. Robert Brown observed that when he put tiny pollen grains on the water surface, they never remained stationary. Nobody knew what caused this vibration that didn't seem to have its origin in the grains themselves, but in some property of the water. Using the results of his previous paper, Einstein offered a solution to the mystery of Brownian movement. He proved that the erratic vibration of the pollen grains is the result of the continuous collision of thousands of objects much smaller, that are nothing else than the molecules that make up water. That is to say, the combination of atoms of hydrogen and oxygen. For the first time, someone had proved that a natural phenomenon offered the opportunity of observing atoms in action. In just a couple of months, the unknown clerk from Bern had proved the existence of atoms and suggested the possibility that light was made up of particles. What Einstein didn't imagine was that the combination of these two discoveries would unchain a revolution that would radically transform our image of the universe, with consequences he would fight during his whole life. We are all familiar with the atom model as a small solar system proposed by New Zealander physicist Ernest Rutherford in 1910, with the nucleus at the center and the electrons freely orbiting it. The only inconvenience of such an atom is that it couldn't exist in nature. According to Maxwell's electromagnetic theory, the electrons in an orbit would emit electromagnetic waves, losing energy and falling in spiral towards the nucleus. In less than a millionth of a second, the atom would disappear. In 1913, Niels Bohr, former goalkeeper of the Danish soccer team Akademisk Boldklub, was also a physicist, and at the time he worked in Rutherford's laboratory. Bohr suggested that inside the atom, the electrons wouldn't collapse if they were forced to spin in fixed orbits. Even though Bohr couldn't explain which mechanism stopped the electrons from freely spinning around the nucleus, his idea wasn't discarded because it explained an ancient mystery about matter. Since the 19th century, it was known that if the light emitted by different chemical elements was split with a prism, the result was a pattern of colors very different for each one of them. Something totally incomprehensible, but that served, for instance, to discover that the sun is basically made up of hydrogen. Bohr discovered that the origin of this strange phenomenon is precisely in Einstein's light quanta. According to his model, each electron has a certain amount of energy that enables it to remain in a fixed orbit. But if it decides to move to an orbit of different energy, it must absorb or get rid of a light quantum, with energy correspondent to the energy difference between both orbits. The fixed orbits of each element are different, and according to Einstein's paper, the color of a light quantum depends upon its energy. Then, the color patterns emitted by the atoms or different chemical elements are the result of countless quantum leaps electrons take inside them. Some years later, Louis de Broglie, a French duke, inspired by chamber music and Einstein's papers, mathematically proved that the fixed orbits of Bohr's model could appear in a natural way if the electrons inside the atom didn't behave as spinning particles, but as vibrating waves. The orbits allowed to each element would be like possible notes a musical instrument can generate. Besides, de Broglie concluded that any particle is in some way a wave. Something experimentally proved in 1927, when the physicist George Thomson, son of J.J. Thomson, who in 1897 discovered that the electrons were particles, proved that electrons are also waves. When in his 1905 paper Einstein declared that sometimes light behaves as a wave and some other times as a particle, he was the first one who realized that physics was compelled to find a way to conciliate these two apparently contradictory concepts. Let's think about some of the most common examples of waves we know: sea waves, and of particles, sand grains. The main difference between them is that a sand grain always occupies just one place in space, whereas a wave is able to extend itself on a bigger area. For us, particles and waves are as different as sea and earth. To appreciate the implications of this bipolar disorder of the microscopic world, let's try to imagine what would happen if we projected small objects against a solid surface with a couple of tracks very near the center. Nearly half of the projectiles would cross through the right crack and the other half through the left one, forming a pattern with two well-defined bands, separated from each other on the opposite wall. Now, if instead of throwing small objects, we projected a wave through the cracks, it would split in two and the new waves would superimpose one over the other. If we drew their intensity when arriving to the opposite wall, we would obtain a pattern with several bands known as interference pattern, very different from the pattern the small objects would form. Now let's see what happens when we perform the same experiment at a microscopic level. These are the real images physicist Akira Tonomura obtained in 1989 by throwing electrons one by one through a double crack and registering their final position on a TV screen. The first interesting thing is that each electron falls on a different place, apparently at random, which is quite strange, because in principle all of them are thrown in the same way, and it would be expected that they arrive more or less to the same place. But there's something even stranger. As more and more electron impacts are accumulated, on the screen begins to appear a notably different pattern to the one that would be formed if electrons were particles. Instead, it's just like the one produced at a microscopic level when we observe waves. How does each electron know it must form an interference pattern along with other electrons? The waves produce this pattern because one same wave can go through several cracks at the same time. Would this mean that in some mysterious way each electron is capable of being in more than one place at a time, and that its behavior is really random? Bohr and most of the physicists who, based on the revolutionary idea of Einstein's, built quantum mechanics, the theory we use to study the microscopic world, answer this question affirmatively. To them, the universe has properties so strange that we don't even have words in our daily language to describe them. And besides, it's ruled by random. But despite experimental evidence was more and more convincing, Einstein refused to consider this possibility during his whole life, to the point that in a 1951 letter to Michele Besso, a friend from his days in Bern, he admitted that after 50 years of meditating about this trouble, he had concluded that he really didn't have any idea of what light quanta were, the same he had proposed in 1905. In May 1905, according to the letter Einstein had written to his friend Habich, his fourth paper was still a rough copy. But by June 30, it already was on the desk of the Annalen der Physik editor, Max Planck. Even for a physicist, the title didn't sound very appealing. On the electrodynamics of moving body. Nevertheless, today it's considered one of the most important scientific works in history, because in it, Einstein exposed for the first time what years after would be known as the theory of relativity. Everyone has heard that the theory of relativity was proposed by Albert Einstein, but very few know that it wasn't the work of this nice old chap, declared enemy of comps and conventionalisms, but the work of the 25-year-old man that went every day to work in the patent office in Bern, wearing jacket and tie. The reason of this misunderstanding is that when the theory of relativity became worldly famous as one of the modernity symbols of the new society emerged from the First World War, Einstein was already a respected professor at Berlin University and hadn't been a clerk for more than 10 years. In those times, many writers, philosophers, and artists thought that what Einstein had done was to scientifically prove that everything is relative, and they used this term to explain new artistic styles, new philosophies, and even new attitudes of people towards new cultures. But the theory of relativity doesn't have anything to do with this popular idea. Its field isn't society, but nature, and though it isn't useful to explain jazz or cubism, it did transform completely our conception of the universe. The name of this theory wasn't even Einstein's idea, but Max Planck's, who started to call it like this in 1906, due to the importance that he gave to an old principle discovered by Galileo around 1630, called precisely the principle of relativity. To explain this, Galileo proposed we imagine a ship moving at a constant velocity through a calm sea. Being inside the cabinet, without being able to look outside, we wouldn't know if the ship is moving or immobile. In the same way, we can't feel the Earth spinning on its axis and around the Sun. In both cases, the reason is the same. In nature, velocity isn't something absolute. Velocity is relative, and it always depends upon the point of view of the person is looking at it. Galileo emphasized that speed wasn't the intrinsic property of an object, but the expression of a change in position in relation to the objects around it. That is to say, there isn't any experiment that allows us to know if we are really moving or not. For example, when we travel in a vehicle, we can also think that that vehicle is moving at a constant velocity and that the city doesn't move, or that the city is moving and the vehicle is immobile. Everything that moved in nature seemed to obey the principle of relativity. Until by the end of the 19th century, Maxwell's electromagnetic theory and a series of experiments showed that there was something that refused to do this: light. Unlike the rest of velocities measured in nature, the velocity of light seemed an intrinsic property of it, because it is always of 300,000 kilometers per second, regardless of the motion state between the object that emits it and the observer that detects it. For instance, light that comes from outer space comes always with this same velocity. Through galaxies and stars, get far away or come closer to us at great velocities. Einstein once said that he had spent a whole year trying to figure out what was the meaning in that velocity of light was something absolute, and at the same time, Galileo's principle of relativity functioned with everything else. Until one day, discussing with his friend Michele Besso, he concluded that the only thing he needed to do was to be brave and challenge one of the most deep-stated concepts of our common sense. He proposed that time cannot be defined as something absolute. Time is relative. Let's imagine we light a candle in the center of Galileo's cabinet. Light would travel at 300,000 kilometers per second, both to the right wall and to the left wall. Being inside the cabinet, we would see light reaching both walls at the same time. But if we look at this event from land, though light would travel at the same velocity of 300,000 kilometers per second towards both walls, left wall moves towards it, and right wall moves away from it, so the first wall would get lit before the second one. What happens really? Do both walls get lit at the same time? Or does one get lit first and then the other one? The answer is that both observations are true. And the order in which two events occur in the universe is not absolute, is relative for the observer, and so our concept of time is relative too. As the velocity of light is extremely high compared to the velocities we know on Earth, because in fact, one of the results of this theory is that nothing can travel faster than light, the effects of relativity are practically imperceptible in our daily lives. But the relativity of time is verified every day at the modern laboratories of particle physics. These places have accelerators where particles are made to collide at a very high velocities. The result of these collisions is the creation of other particles that very often have very short lives of small fractions of nanoseconds. Nevertheless, as their velocity is almost the same as the velocity of light, from our point of view, their life is long enough to be recorded by detectors around the point of impact. time goes by in a different way according to the relative velocity of the observer. We are used to think that there's a now for everybody, as if present were the same in every place, and one clock could keep the hour of the whole universe. What Einstein found out is that everyone has their own time that goes by in a different way from the time of others. And since there is not just one time in the universe, present, past and future are relative to a certain point. This, by the way, is one of the few results of the theory of relativity that Einstein himself moved from the scientific field to the human field, when at the end of his life he knew about the death of his dear friend Michele Besso. In quitting this strange world, he has once again preceded me by just a little, he wrote to his widow. But that doesn't mean anything. For we, convinced physicists, the distinction between past, present and future is only an illusion. On September 1905, Einstein wrote again to his friend Babbage, inviting him to come back to Bern and become, like him, a slave of the patent office. "You have to work 8 hours," he wrote him. "But think about this. The day has 8 more hours to walk around, and there are also Sundays." At the end of the letter, Einstein told him that he had thought about something so strange and attractive that God surely was laughing at it and was taking him on the wrong track. On September 27, a surely surprised Max Planck received a new paper of only 3 pages from the unknown clerk from Bern. The title was, "Does the inertia of a body depend upon its energy content?" Einstein begins by saying that the results of the previous investigation had led him to a very interesting conclusion, and after some more or less simple equations, he concludes with this formula. The same formula that today appears on every physics textbook, but that everybody knows as energy equals mass times the velocity of light squared, physics' best known equation. Einstein's very interesting conclusion is that all objects, just for the fact of existing, have energy stored in their mass, even though they remain immobile. This is a very revolutionary affirmation that contradicts traditional physics, which is still taught in schools, where the distinction between the concepts of mass and energy is very emphatic, and energy is only attributed to isolated objects when they are in motion. What Einstein really discovered is that space and time, 2 things that seem so radically different to our daily experience, are truly very close related. It is possible to combine time with the 3 known dimensions of space, interpreting this as the 4th dimension of a new representation of reality. If we consider time as another dimension, it makes sense to talk about movements in time as well as in space. Although it seems strange, even if an object is stationary in relation with everything around it, it's moving towards the future at the exact velocity of a second per second. As well as we acquire energy when moving through space, this new stationary energy discovered by Einstein is due to the unavoidable movement of all objects towards the future. At the end of his paper, Einstein speculated that the mass of any object could be transformed into energy. Regretfully, one of the most forceful experimental proofs that he was right was the huge destructive power of atomic bombs. The enormous amount of energy liberated is the result of the transformation of a tiny part of the mass of the material that causes the explosion. Einstein's image and his equation are frequently related to the atomic bomb. But even though it was him who informed President Roosevelt in a famous letter about the possibility of producing this weapon, he didn't have anything to do with its design and construction. In little less than a year, and with just the help of long conversations with its friends in Bern, the suggestions of Mileva Marek, his wife, and the reading of some physics books, Albert Einstein had published the 5 papers upon which 20th century physics would be based. On a heuristic point of view about the creation and conversion of light, a new determination of molecular dimensions, first and second parts on the theory of Brownanian movement, on the electrodynamics of moving bodies. Does the inertia of a body depend upon its energy content? Years later, he would turn his theory of relativity into a theory of gravitation, giving to science the possibility of understanding the universe as a whole at last. Thanks to Max Planck, he would obtain what he had longed for so long, a job as physics professor at Berlin University, and would become more famous than Charles Chaplin. But by the beginning of 1906, Albert Einstein got just one direct benefit thanks to the publication of his 5 papers. The technical expert of Bern Patent Office, 3rd class, became the new technical expert of the Bern Patent Office, 2nd class. Narrated for Canal 22 by José Luis Palomera de la Re, with the collaboration of Liliana Torres.